Good morning, everybody. This is Dr. Chow, Eric Chow. I will get started for our programming language course. So far, I didn't see anybody join this session yet. Maybe there are some technical issue or something, but I'll get started for this course. Today, we are at week 1, session 1, and I'm trying to finish the chapter 1, the introduction for programming language. And I'll get started soon. So for this course, right here, I would like to introduce the syllabus and then discuss some classroom issues. So first, what will you learn from this course? This course is organized in actually 3 units, but the textbook we have is actually have 4 units. So the first unit is for the fundamentals. And the fundamentals, we teach you the basic concept about what is programming language and the programming language programmatics. And in this part, we teach you what is the mechanism of designing a programming language and make it work. And second unit, we are talking about the core language features. And the language, as you may know, it can include the data structure and also the algorithm part. So basically, we will introduce the control structure, including conditional control, decision, selection, repetition, iteration, and recursion. These are 2 parts, and then that's in chapter 6. And in chapter 7 and 8, we focus on data structure for data type and the data structures. And in chapter 9, we go back to the control for the programming language. And chapter 10, we introduce object-oriented programming. And after that, we have several programming paradigms to introduce, but we will only pick the concurrent programming as the topic. And unit 4 about the programming environment and hardware, we will omit because our course is only for 8-week course. So basically, we don't have that much time to cover everything in such a short time. So I try to focus on the Unit 1, Unit 2, and Unit 3 comparison of programming language. We will be very likely just cover the chapter 13. So basically, I call this course as the computing model for the programming language. And basically, we are talking about the programmatics of the programming language as the name for the textbook that we choose. About the grading of the system of this course, we use the accumulated point system. So basically, each quiz, each homework, or each project, you will be assigned for certain points. And then you will sum up with a total point. And that total point will be divided by the base point, the maximum base point. And you will get a percentage score. Right here, I say the total amount of points that we will be dividing is the base point. That means that your total point may be more than that, because we will give you some bonus point from time to time in each exam and quiz, and also for the projects. And for the term projects, I have the recorded message regarding 3 options over there. And basically, each one, I mentioned like 100 points or something in the video, but that's not actually accurate. So we will use a total of 500 point system, and then a bonus point of 100 points. So basically, you can forget about whatever I covered in the video regarding the number of points you will receive from the project. At that time, I'm thinking of a total point of 100. So that is actually wrong. I later adjust the weight for each project. So basically, there are 3 options that you can pick, and each one, the maximum score you will get is 500. And I may just judge on your technical difficulty and whatever effort you have spent on that project, and maximally will assign at most 100 bonus point. And this 100 bonus point is not included in the base point. So actually, you may get more point than what we will be used as the base point for the maximum point you can get from for the quarter. And this so far with these three term project options, and this year I would like to include the fourth option that actually is a free option. As long as you work on certain term project of your own, the topic that you can choose by yourself, and then we will accept it as long as it is related to programming language. I will accept it as a valid option for you to choose. And then you can when you actually in the third week, you need to turn in the proposal for your term project. At that time, please indicate in your proposal that you are choosing the option 4, and the option 4 is not on the term project description, or I do not provide any option item over there. The reason why I would like to open this number 4 option is that from the experience that I have last year, basically, not everyone has the background for in C, C++ language. So this year I would like to open up a certain free project that you can work on, that you can choose the language that you want to learn, or a language that actually you feel most comfortable to work on a scalable project or something that meaningful for you as a term project, and later on when you go for a job interview, that you can feel proud about yourself and you can present to the interviewer about what you have done in college. So that's the purpose that I would like you to focus on. So the term project, the purpose is to help you to build up a good portfolio for yourself, so that when you do interview with some company, you have something that you can rely on and you can actually present to the interviewer. So here is the last year's point system, and each one will have certain point. For the discussion, for the homework, for the quiz, there are certain point, and at the end we'll sum up the base point. Last year is 255, and this year may vary, but we will base on that total number of points, and then we will have a total point that you receive, and then divided by this base point, and by percentage we will assign your score. But remember that each one of them we may assign some bonus point for you as long as you work hard. So I would like to have give you an environment that you can actually work hard and without any worry about your own grade, but you actually can learn as much as possible. So here is the description of the programming language course and the relationship with other courses. So right here I list down the core course for computer science. And as you may see, there are 4 tracks that I picked. The right hand side, the blue one, is actually the computer architecture and hardware parts. You may learn assembly, computer organization, computer architecture, microprocessor lab, and this is one track. And second track is computing track, is red one, logic design, finite state machine, automata, computational theory. And third one is the software side. You have Unix scripting, operation system, and Linux or Unix lab. And our core right here is the programming and the programming and language track. This track, some people also call it algorithm track. So basically, you need to learn Java, Java 1, Java 2, Python, Python 1, Python 2, C, C++, and then move on to data structure and algorithm analysis. And beyond that, you will learn some basic programming language theory, computational model, automata, and then you move on to this course, programming languages. So this programming language actually combine the knowledge of automata, operation system, and computer architecture, and to support the construction of a programming language and also a computing model. And later, these knowledge which can be used for the real compiler design for language translation and machine code generation. And another purpose for this course is to pick a language for you to use in your project. So right here has a detailed flowchart for you to trace, to follow, to pick a language for yourself. So this is our syllabus for this quarter. Now I'm going to turn to different slides. Let me see, textbook and software. For the textbook, we use this book, Programming Language Pragmatics by Professor Scott. And I believe he's with University of Rochester. And this book has many different versions. And I have the PDF file for the third edition. And right now we are using fourth edition. But if you need the third edition PDF, I believe I have a download link in our course material section. And if you cannot find it, let me know. I can send a PDF file to you. And you just send your message for the book PDF request to my email. So now I will write down my email address in the whiteboard. So right here, my name. And to reach me, you can call me by phone number 510-304-9428. My email address ECHOU, E as Eric, CHOU, my last name, 510, which is my area code, at gmail.com. Okay, these are my phone number and email address. And actually, I do not offer the fixed office hour this year because last year I'm there for a long time, but nobody actually reached up. So this year, what I would do is actually you can call me at any time and then leave message, or you can actually just send me some message, some email to my email address, and then if I got your message, I may call you or may set up a video session using this tool, Zoom.us. We can have an online session to help you to solve your problem. So make sure if you have some question you want to ask, just call me or leave a message for me. And also you can go to my my Facebook page, http and then www.facebook.com/DRERICCHOU. So this one is my page. Okay, here is my group page in Facebook. So if you make requests, I will add you as a friend, and then we'll sign you up, put you over here. And over here, actually, I have a lot of messages I'll post regarding related to programming language and computer science as a whole. And some past students actually also join this group and share some idea. So that's another way we can communicate. And you can also send me some message, and I will actually handle it and then reply your question as well on the Facebook as well. So this one, just I have a space here. Just again, you can come here with the facebook.com and then my name, Dr. Eric Chow, and you can just send a friend request to here. I will grant it for any student from this course. So this is our textbook, Programming Language Pragmatic 4th edition. And there is a companion website you can visit for the material. Okay, let me check if there's anybody join this course. Okay, we have another student. We have Daniel. How are you? Let me type to him. I don't know whether he can talk or not. Hello. Can you talk? I should have set up it to be available for student to talk. Oh, I'm sorry. Okay. But do you hear the first part? Okay, good. Now I'll continue. I finished the syllabus and also the textbook. Did you get that? Okay, good. Now I'm going to continue. So this is about the textbook. And this textbook, we will just mainly use the Unit 1 and Unit 2. And also Unit 3, we will only cover the 13 chapter concurrent programming. Now let's go to our website for our course. So website for our course right here. Each week you have a certain folder, so you just click on this. It has the whole thing that you need. Okay, so for the study material, we have instructional material. So basically, you can download the presentation slides, and also actually each one for one session. And then you have this some lab you can work on. Okay. And for the lecture that you for these slides for the lecture, you can come to here. We have the last year's video, so I will try to record every session. But if somehow you don't have time to join our session, I will give you some link, so later you can watch the video from YouTube channel. But also, if you still not answering all of your questions, you can come here for a different session that is recorded for the last year. Some of the material that I covered in last year's session, I may not repeat this year because I try to pick different material. So for example, here we have a section for, let me see, right here, we have a section for Python for calculator language, and we have a section for lexical analysis. We have a session for this one, a Python calculator project. This one is actually a extra session. I call it session 3. Actually, it mainly covered the tool. Let me show you. Actually, it's covering the actually it's covering Lex and Flex and Yek. That's Yek and Python. Let me bring up my whiteboard. So basically, because we are talking about programming languages, so we actually will talk about the design of a compiler as well. So for a compiler, basically you will take in your language. Say we have a C, C++ language, and then you need to first work on the lexical analysis, and then you work on parsing. Okay, out of lexical analysis, we introduce the tool called Flex. And then parsing, we introduce the tool called Python. And Lex in the past also called as Lex, and Python also called Yek. Yet another compiler. Okay, and this tool this year I won't repeat, or I will not repeat. Okay, so what you should do is like come to here and work on this different project that I talked about last year. Instead, if I have extra session, I will not cover this year. In this year, I will actually cover different things. I will try to give you another session 3 that is not on our schedule. In the session 3, I try to cover the tokenization. So basically, that will read in a file, say .c, that's CPP file or the Java file, whatever file or any text file. And then the second, I will cover BNF form or eBNF form. Okay, later we will discuss this, but basically I'll cover these three stages. This one, and last one, regular expression. So basically I may give you 3 extra sessions that's not listed in our 2 sessions per week schedule. But I'll try to introduce this, and also the language I'll pick will be on Python. Okay, and the previous last year's session I introduced Flex and Bison. That's in C++ language. I believe that most of the students I know, probably only 10% or 20% has the C and C++ background. So this year I try not to make you too stressful. So I pick this different track, and I would do mainly use Python as an example. And I will show you the slices over here, just briefly. And here I have different session here. So for example, Python. So I'm sorry, for anybody's tokenization. So basically, this year I would have 3 extra sessions. I may do that on the first 4 or 5 weeks to cover this. First one is tokenization, how you can read in a file and then generate tokens using Python language. So this will be very useful, for you just to help you to learn how to process file when you read in some text file of different language or different format, and then create a token for it. Okay, so here is one session, generate a token. Second session, I'll cover eBNF. This one, is there some question? Hello, we have another person. Welcome. Okay, this one for eBNF. eBNF is a extended package NOR form, and this one actually is used to design the grammar or the rule for the tokens. So basically, we are trying to give you some idea of how to create a pre-processing for the lexical analyzer. And this is the complete text processing to generate tokens. So this year, I try to give you the idea of this eBNF, and basically tell you how to design some pre-processing for the grammar part, and we will come back to this later, okay? But the most important part here actually is trying to teach you how to design the Becker's NOR form, and try to design this, formulate this into regular expression. I'll show you the regular expression, the syntax diagram, and then regular expression, the regular expression part. And after you formulate it into regular expression, we'll talk about the third, we'll talk about the third session, regular expression in Python. This one teach you how to design in Python language, how to handle regular expression. So these are the 3 extra sections I will cover this year. And last year, as I said, we are on different track. We talk about the Python and Flex. And if you feel interested in C++ language, you're still welcome to look at that. And these different extra sessions will give you some idea of how to organize your own idea and create your own term project. So that's the purpose why I would like to give you some HR session, but it is not required for you to attend, so it's optional. And my quiz or homework is not related to that, but I will give you HR knowledge to learn. So far, any questions so far? It should have allowed you to talk, chat during class time. So if not, let me know. If you cannot turn on your microphone or you cannot speak, let me know. I try to be more interactive because it's hard for me to come back to this control panel to probe you, to figure out whether you have any question or not. Anyway, okay. This is about the HR sections. So after that, actually, you have 10 project to work on. So for the 10 project, as I said, this year, not limited to the 10 project option 1, 2, 3. There will be a option 4 that you can choose that I have not listed down here. But the option 4 is very simple. You just work on anything related to programming language. You feel that you would like to organize it as a project that you can present it to whatever interviewer interview you will go into in your company or something, and then help you to build a project that is presentable. And you send it to me with your presentation file, PDF file, PPT file, or your project file, C, C++, Python. It's all accepted. Or you create a video link in YouTube for me to look at your presentation. That's fine. The whole purpose is help you to organize your own knowledge you learn from this course and also make it presentable to whatever future employer, yeah, I'm sorry. So it's about the term project, and weekly, you just need to follow whatever we describe in the weekly notes. Next, I would like to introduce myself. My name is Eric. Actually, I graduated for my college. I graduated from National Taiwan University, and then I came to United States to USC, University of Southern California, located at Los Angeles. And then I work on my main PhD thesis is on VLSI, sensory information processing. Okay. And my PhD dissertation is right here. You can still come to the USC website for my dissertation. So I would actually just pause on the chat here. So the reason why I'm talking about my dissertation is the topic I picked actually is on artificial intelligence and actually on neural network, recurrence neural network. So it's actually a computing model. And at the time I attended PhD, I'm using the analog approach, building the chips, the analog chips, to build a neuron, and another neuron. They actually send information to each other, and then handling the pattern recognition. Okay, pattern recognition. And this, I call it as a computing model. Okay, and with that computing model, I actually built some MATLAB code and also later C language code to do some computation. So basically, this is related to the computer programming language. We need to first have a computing model. Some model we want to do computing. And based on this computing model, we generate some programming paradigm. And then we pick a language and a machine. Okay, to do computing. So this programming language is related to here, but the source or the key idea is to find your computing model. So for AI, now you hear neural network, fuzzy logic, and you may hear some other term or DNA computing. That's different way of modeling a computing. And computer science is to map your problem in your computing model. So computer science basically is to map a certain problem and you solve it by certain computing model. And the language and machine is to support the problem solving for this. So basically, I look at this course as how to build a language or use the machine to help you to solve problem. And problem solving part, the algorithm and data structure, you have learned the basic knowledge in your sophomore or junior year in college. So by here, we try to give you more advanced knowledge. So in the future, you can, based on your knowledge on programming language, move on to AI or move on to solve the computing problem and also move on to compilers. Okay. And the time I work on my PhD program, the neural network, we can only put a few neurons onto a chip. At that time, using the analog approach, probably we can do like 20 neurons on a centimeter by centimeter die. That's about a good size at that time. And we use like 0.5 micron technology. But right now, the IC had already moved down to 10 nanometer technology, 7 nanometer technology, or now even that, or will go to 3 nanometer. Okay, currently 10, 14 are in production. Okay, so nowadays, and at that time we are actually working on analog neurons. But now for Google, you may hear of Google's tensor processing unit. Okay, what is tensor processing unit? It's also related to neural network. Tensor processing unit. Okay, here is the tensor processing unit. That's for AI, big data computation for learning. So a single board can replace a whole cabinet of computers. And this one is used in the AlphaGo project. AlphaGo to beat the human Go players. Okay. And actually, this project will actually, there are quite many companies working on this sort of TPU or AI chip, including Intel, NVIDIA, and several companies. They work on different flavor of the AI chip right now, and they all based on the RNN recurrent neural network approach. But at that time, we can only put 20 neurons in there. As the processing technology moved up, actually one dimension about 1,000 times more space, smaller for the neuron. And then totally, actually, 2 dimension, actually, you can actually have a gain of almost up to 1 million times smaller for the neurons. So basically, at like 20 something years ago, we can only put 20 neurons here. But with digital neuron, right now, probably up to 20, like 200,000 neurons can be put onto a single chip. So the computation is way much bigger now than before. Okay. So that's the work I work on when I was in PhD program. Now let's go back to our chapter 1. We will officially start our chapter 1 now. Let me ask them a question. So any questions so far? Okay, we'll get started for the chapter 1. So chapter 1 is Introduction to Programming Languages. So here we have a lot of different programming language. And instead of the installation and daily use, JavaScript has the largest amount because there are so many websites, and a lot of websites right now doing client-side computing. And then Python is also very popular, Java, and Ruby on Rails. These different languages are actually more related to websites. And nowadays everything is on web page, so or app on your cell phone. So this different language has more installation than the core language like C, C++ now. And that's high level language. And the high level language is to use a English-like language to help you to do programming. And but the real language that machine can understand is actually the machine language, and it's actually not readable. So the programming language course that we have right here is to help to build a machine or a system to help you to process those different language and convert them into the machine code. That's the job of compiler, and also to study the computing model to help you to solve problems. So, and then in the middle, we have the assembly language. So they are high-level language, assembly language, and machine language. And assembly language is in between the machine code and high-level language. So basically, it's an instruction level language. So basically, in terms of programming language, we actually has one important thing for each machine. It's called instruction set architecture. For example, we have x86 architecture. We have Intel's i7 core architecture. So that's so-called instruction set architecture. And another thing is instruction set architecture compatible. So one series of i7 processor may be a few hundred different chip models, but they share the same instruction set architecture. So everything you develop on the same instruction set, say JavaScript, or your Python code, or your C, C++ code, will be compatible on this instruction set. And then under that, it actually is machine code. And basically, this is the idea of why the assembly is important, because this same instruction set architecture will be shared by different chips, and they have different processing speed, different clock rate, but they will share the same instruction set architecture. They run in different speed, in different resource, different amount of resource, but their code is compatible in the instruction set. So that's why assembly language is important. That's why this assembly code is important. And in terms of the most popular language in 2016, Python is number 1. Second is Java. This is not by the installation of the compiler or assembler. It's the the percentage used by the programmers. So basically, if you pick Python, Java, C, C++, and JavaScript, these 4 or 5 language, probably you will be able to work for most projects. And other than that, other languages are like application-specific languages. And right here is the timeline for the development of different languages. The first language, actually, the first high-level language being designed is this Fortran. And Fortran is short for Formula Translator language. And Fortran language is called Formula Translation. And this Fortran language in human history is so important. With IBM 360 machine, these two things achieve one thing in very, very important in human history. That is, these two things in combine help us to send rocket to the moon. So if you don't like Fortran language and feel that it's so buggy, it actually achieved this in human history. So it is the first language used for scientific calculation, and a lot of C language library actually is brought from Fortran. And even nowadays, the most advanced scientific computation, something like your printf function, those formatted printout still follow the old standard that's set up by Fortran. So that's the one very important language to have in human history. So there is an imperative language family: Fortran, PL1, C, Modular, and then Ada, and then go to C++. This is the main trend for one family language, and they are object-oriented programming language, they are functional language, concurrent language, logic language. These different languages are in different programming paradigm, and later we will talk about what is programming paradigm. So why are there so many languages? Number one, because of the evolution. Second, for social, economical factors. For example, proprietary interests. One of the good example is language C#. Okay, C# actually is similar to Java, but it's actually developed primarily by Microsoft. Even though it's made public right now, but Microsoft still behind it. And Java, as we know, it actually is mainly supported by Sun Microsystem, and then now by Oracle. So there are also some social economical factors as well. And some company, they just want to own their proprietary language. And then they are special purpose language, and they are hardware special language. And this we will give example later. The next one, what makes languages successful? One important factor is the language must be easy to learn. If the language is so hard to comprehend, then very few programmers will be able to learn it. So make things easy is one factor, very important to make things useful. Second, to be impressive and also powerful. And that is very important. If your language cannot do too much things, you don't have enough library to support, you don't support good GUI, good looking, stylish GUI, graphic user interface, then the language itself may not be that useful. Okay, and then also need to be easy for implementation. Then the compiler designer and tool developer is able to develop that tool easy and fast. For example, one language that is so successful is Python. Python is basically a open source language. So a lot of contributors help to build Python to make it successful. So Python, why it moves so fast compared to some language like Java or C, C++. Those language, some of them has historical reason, some of them is owned by certain company, so the development is not as fast as Python. And Python, every year there's a Python conference to discuss new proposals and adopt new programming language features. So Python moves so fast, and because of the open source feature, and every year a lot of new contributors contribute different package to Python, so make it this language so successful. So easy to implement and have good resource is also very important, and compilation time is also important, and the cost is also important. For per installation cost is also very important. And the language is for what? It's help us to think. So basically, as I mentioned previously, we actually need to come up with the computing model. So basically, the language help you to summarize your idea in your problem solving process, to help you to organize your idea and put it into a working format to allow the machine to process it. So you need to combine your knowledge in computing model and also to write it down in a way that the machine can handle. So language design is an art, including the factor of evolution and maybe of certain special purpose, and is also related to personal preference. And one important factor is how expressive it is, and need to make it easy to use for novice people, and easy of implementation, and standardization. Standardization is also important. For example, some language like C, C++, in early days, there is no standard. It was developed in 1970 for Unix system, but the standardization had to be available until around 1985 for the first ISO standard. So when I went to college, there's no standard for C, C++. There's a compiler for Microsoft installation. There's another version on Unix version, and there's yet another version called Turbo C. So there are so many different implementation. The library is not really compatible. Even the number of bits are different. Some implement integer as 16-bit, some 32-bit. So it's very confusing at that time. And later, the ISO come up with standard definition for those integer lengths. And open source is one important factor, and compiler design is also one factor for the success for a language. And also the last one, whoever support it, the patronage, and also economic and the habits, the inertia that programmer has. Now, lecture 2, why we study programming language. So basically, you need to know what's the application. Whether you want to do system programming or numerical programming or embedded system, the application that is the reason, one of the most important reason why you choose a language. So in modern world language, we have network language that help to build a server or client-side language. So you have Java, JavaScript, Ruby on Rails, Objective-C, PHP, and these different language. And there are mobile language help to build the apps, your Suite system, your Microsoft Visual Studio, and your Android system and Android Studio. And they are markup language for your XML, HTML, CSS, and JSON language. You have database language, Perl, Ruby, Python, PHP, SQL. You have numerical computing language. You have R language, MATLAB, Scoop. You have Python. You have desktop programming language, C, C++, C#, Java, and Python. You have hardware discrete language, VHDL, Verilog, and System C. And lowest level, you have electronic modeling language, EDIF, HSpice for simulators. So these are different language, and they can be a general purpose language like C, C++, Python, Java. These are general purpose language. There are application specific language like Verilog, VHDL, and the Scoop, R language, or HSpice. And these different language, they all need the programming language knowledge, and they all need the compiler design. And that's why the compiler design and this programming language course knowledge is very important. It will help you to develop the tool in different application, to develop the app kit, to develop a electronic device modeling language, EDA business, to develop a certain big data data analysis tools. So that's why you need to learn the core knowledge for programming language. Okay, this one I will skip. Another reason to make you a better use of whatever language you have. To learn programming language, you will know about different data structure, different feature that you have in your language, and why you need to have those different features. And second purpose is to understand the implementation cost. So we do this, how much computation we have, and if we use this, how much time we need to spend. So we have a comparison of different way of implementing things, and would end up how much computing costs we need to pay. And third one, figure out how to do things in language. And fourth one, to figure out, whether the language is support or not supported it. Some languages don't support certain feature, and it may not be a best language for you to do certain application. So the study of programming languages are basically trying to give you the answer of the following topic: what is available in a language, and what is not available in a language, and what is good about a programming language, and what is bad about a language, and what is the real use for a language. Trying to answer these different different questions. So when you pick a language, you know which one should I pick. Now we are on the programming paradigm and spectrum. So basically, the computer scientists group language into two main categories: declarative and imperative. Okay, these two are actually a little bit different. The first one is by deduction, or some people call it inference. The other one is statement by statement. We call it imperative. So this imperative language, Neumann model, object-oriented model, or scripting model, we all know this quite well. They share the same common structure. So basically, you can also call this as structured language or object-oriented language. Each one is based on statement by statement code, and also based on the idea of for loop, repetition, and decision, selective, those different statements. So these language, in some sense, the grammar are similar. Declarative language, they are different. They have the functional programming, they have data flow programming, they have logic programming. So basically, these are of different paradigm. So first, let's look at the declarative language. For example, for logic programming, we have Prolog. So a friendship is defined as a friendship between X and Y, two persons, is actually defined as a like relationship, say X like Y and also Y like X. Then we define they are friends. Okay, so the left-hand side is actually a non-terminal term. Right-hand side can be a non-terminal term or a terminal term. So X and Y are friends is defined as X like Y and then Y like X. This is a rule or reduction rule. And this rule can verify by another rule or by the facts. So here are the facts. Jiang like Jane and Jane like Jiang and Jack like Jane. So if we ask whether Jiang and Jane are friends, we will put the X and Y over here. One is Jiang, one is Jane. And then we will evaluate the system, actually Jiang like Jane and Jane like Jiang. Yes, we found the two facts, Jiang like Jane and Jane like Jiang. So Jiang and Jane are friends. But if we check Jane and Jack, and we will find actually Jack like Jane, but not Jane like Jack. So they are not friends. So if your programming is done by logic reference reduction, and actually this we call it logic programming. So in logic programming like Prolog, you don't have statements by statement execution flow. Instead, you have this logic reasoning process to help you to solve the problem. So that's one programming paradigm. We call it logic programming. And it's actually a declarative language. We call it declarative because you need to declare each rules and all the facts. So that's one way to do it. Second one is this data flow programming. For example, like in MATLAB simulated model, the whole modeling is driven by data flow. There is no instruction. There's information source. Say we have an image come here, and then we actually figure out what are the files available. And each one we read in the image. So we read image and then doing processing using smooth image. This can be a filter or can be a subroutine to help to solve it. And then at the end, we generate some Y images. So basically, you have the data flow to different processing stage. And then at the end, we analyze the result. This is called the data flow model. And some language, especially image processing or audio or speech processing, all follow this data flow diagram approach. So this is another language style called data flow. Third one is some language like Lisp or Scheme or Haskell. It's called functional language. It's based on the Lambda calculus or the function call function structure. This is called functional programming. So A function called B function, B function called C function, C function called D function. So one by one, it is by the functional call structure. And because the functional call is organized in some systems similar to the rule-based system. So these three, we call it declarative languages. There are other models as well, but these are more popular models for declarative language. Imperative language by itself is based on the von Neumann programming model. We call it accumulator model. Basically, you have a control unit, you have a arithmetic processing unit, and it access memory. So whatever language based on this model is called von Neumann programming model. And this is the basic statement by statement model, and also the structure programming that come with if then else structure, come with for loop, while loop, come with the functional code, procedural code. This kind of model is von Neumann programming model. And this model can also be put into another paradigm called scripting programming. The basic language structure are the same, But scripting programming is processing the statements one by one. So it can have a temporary or intermediate code, model code, bytecode. And it can also have the virtual machine type of things. But this is actually maybe is on top of manual model, and maybe is side by side have a separate program called interpreter to help you to interpret it. So this is another model, but the language itself is similar to manual model. And third one is object-oriented programming. And object-oriented programming is based on manual programming. There's no doubt about this, but it may come with some new features, say event-driven programming, concurrent programming. When you add this different programming paradigm into there, you need object-oriented programming environment to help you to facilitate the event-driven programming model, and also facilitate the thread control, thread management, the concurrent programming environment. So these three are actually three different models, but the core of it are actually similar. It's the manual model, and that we call it imperative languages. And recently, because of the app application, we start to hear the word block programming. This block programming is designed block by block. For example, we have the Snap or the Scratch. Scratch is developed by MIT. Snap is by UC Berkeley. So they help students, actually young age students, like elementary school students, to do programming, not using the instruction, but using the block, design blocks. For example, you can set pen to certain color. You can switch to some costume. You can play some music or some effects, some variable by certain effect. So this is called block programming, and you can also use the block to assemble the music and process it stage together. And this is done by MyBlock or MIT Inventor tool that help you to design an app in a short time. It is graphical design. It can be data flow model like the Simulink, that is MyBlock case. It can be rule-based as well. It can also be imperative. It can be combined. But for user to design the app or a application or a XML file, you actually use the block instead of statements. That we call it block programming. So right here we have a same algorithm doing GCD, greatest common denominator, or some people sometimes call it greatest common factor. These two terms in mathematical meaning are different, but actually when it comes to programming, actually the method is the same. To find a common greatest common factor or greatest common denominator, they actually share the same algorithm. Here is not the best algorithm we can have, but basically in C, in OCaml, and in Prolog, we do differently. And C is imperative programming, so we know that there is a while loop, if then else structure, and we return some function. OCaml is a functional language, so basically you actually go through the process using the recursive code format. Prolog in a rule-based system, so it's like a predicate with some validation of each predicate, and in a reduction format. So let me check if there's any questions so far. We have, okay, Mikio left. We still have Daniel. How is Daniel doing? Any questions so far? Okay, thank you. I try to give you several, the idea of several programming paradigms and make sure that you understand there are so many different paradigms. And in the future lectures, we are trying to basically give you the idea of how these different paradigms will be designed by the programming language knowledge and also by hardware and software support. And the Unit 3, the comparison of these different language, we will not cover it, but it's up to you to study, and we can finish it within an 8-week frame. It would take like maybe 16 weeks or more to finish that. So this guy, Newman, he probably the most important contributor in computer science so far. Newman was an important figure in computer science. The most important contribution he has is the use of memory in digital computer to store both a sequence of instruction and data was a breakthrough to which Newman made as a major contribution. You may ask the question, why? Memory is so easy to know, then why this contribution to bring memory to digital computer is so important. So the early days when people design from the EE background, when they design a machine, they only know about AND gate, maybe a NAND gate, right? They somehow connected by some OR gate or something, and then later maybe some NOR gate, something like that. So at that time you have number of bit input here, and you have number of bit and bit here. So if you look at the bread box, it's a number of bit into here, number of bit getting out. So basically you are trying to solve a logic problem, and that's it. So you base on number of bit input, output, and the bread box to process it. But this definitely you cannot do programming. But like back like 70 years ago, 80 years ago, you are stuck with this idea. So they build a few board and then take data into there and processing and provide result. So at that time, people only think about, At that time, people can only think about a bread box. Okay, one box, I give number of bit there, and then I get some data out, N bit in, N bit out. But this guy, Newman, tried to help to do this. I give this result to some memory. And then I feed back to certain input. So this become a machine. And then we can add feature into the memory, providing storage for program, providing the storage for the instruction and data. So this we call it the Newman model. And because of this, recursion, because of this, the structural programming is possible. You can start to have if then else, not just a simple combination of simple combination of the logic. And later, actually, they also invent stack, call stack. And once call stack is available, they start to do recursive code. So the recursive function can be implemented because of the stack. And it's also on top of Newman machine. And because of the recursion, we start to have the functional programming. And because of this functional programming, we start to have the idea of abstraction. So because of this functional programming, we start to have the idea of abstraction. And after abstraction, we started to have the idea of object-oriented programming. And then we have the idea of graphic user interface. And then we start to have Windows. And after we have the Windows, we start to know about what can be possible on web. After we have web, then we start to have the idea of apps. So these are the steps that people develop different programming model and different application step by step. And if we trace back to the root, it's coming from electronics. It's coming from electronics, logics. And now, the most important one is this Newman model. That's why it's so important. And IEEE still have a Newman award prize. And it is considered one of the main, most important contributor in programming language and computer science domain. So this one is Newman. And Newman also created a field of cellular automata without the aid of computer. So it's the first self-replicated automata using a pencil and paper. And then because of the Newman model, we have these imperative language, as I said, the introduction of stack, the introduction of memory, and start to be able to occupy our attention. And then we start to spend time on logic and functional language. So this is the basic Newman model. Until nowadays, we still have the control unit, arithmetic unit, and also memory. And it starts from combinational logic, and because of Newman machine, it's possible to build a finite state machine, push down automata, and then tuning machine. So the early day, the combinational logic is like this. You have NB in, you have NB out, and you design logic in there. It's not programmable. And nowadays, combinational logic is still used in adder, subtractor, PLD, this data transmission, encoder, decoder design. And you have the 7-segment BCD. These are, you still can find parts to assemble a board. And here are the finite state machine. You have a synchronous finite state machine and a synchronous finite state machine, mini and more machine. And this is possible only by Newman. And then two model. And later, people are not satisfied by Newman's 0 and 1. So some people come up with the idea of Farley logic machine. So they have not actually 0, 1, they have grade level 45% or something coming to control design. So there is a certain time, like 10, 20 years ago, there's a Farley logic controlled system. Still, there are some washing machine or something using the Farley logic design. And also nowadays, the most important invention for AI, the neural network, the recurrent neural network model. And then DNA computing. So we actually try to do computing, and computing have different model. You have Newman model, rule-based model, Farley logic model, neural network model, DNA model. And to solve those problems, we actually need a paradigm. We need to have ISA, instruction set architecture. So we can map this problem onto the machine like Intel processor or your A10, A11 on your cell phone. And then you need to find a language to help you to solve the problem in the computing model, put onto the processor, and use a compiler. So these are the steps. You need to choose your computing model first, and then find a hardware, and then find a language to support it. Now here we will start the idea of interpretation and compilation. And for comparison, right here, I choose 3 languages: C++ model, Java model, and Python model. Use these three to explain the idea of interpretation and compilation. On the right-hand side, C, C++ is the representative for compilation. On the left-hand side, Python is the representative for scripting and interpreter. In the middle, Java is halfway. It has a front-end processing using compilation, and it compile to bytecode. And then the back-end just-in-time compiler, actually it is a scripting and interpreting environment. So Java is actually a hybrid system. So pure compilation is C, C++, especially C. You host program we compare to target program. So you have and then you have that target program to accept input and provide output. So it is okay to compile C into Java. The answer is yes. And also, it is okay to compile Java into C. It is also yes. The compiler translates the high-level source program into an equivalent target program or low-level machine language program. Pure interpretation is like Python. It's mainly for the scripting language. The early days, the scripting language is used for shell scripting. So you may use the Unix shell language, and those shell language, those are pure interpretation. So they take the statement one by one. And then, okay, let me choose an example for you. So right here, what is compiler and what is the interpreter? So interpreter say, okay, right here, for example, there is a person, I say, how are you? Right, in English. And then there's a guy saying Japanese, they will say, Genki desu ka? Right? It's equivalent to how are you? So this is a translation. And then I'll say, fine, thank you. Right? And this guy will respond, 大丈夫? Arigato gozaimasu. Okay, whatever. So you translate statement by statement. That actually is what? That actually is interpretation. You hear something, you respond. You hear something, you respond. That's interpretation. And for compilation, is you put the whole thing together. So for example, today is cold. How are you? Something like that. And then you put into a whole file, and then there's a translator, and you will translate the whole thing, and you will say, 今日は寒いです. Genki desu ka? Something like that. And then you provide the whole result, put into a different file, and translate into different language, from English to Japanese, right? So that is actually called compilation. You treat the whole thing together and provide it at a whole thing. And the answer, this also answer you, this can be, you can put into, for translation, you can put into this, English to Japanese, you can put it into English to Chinese, you can put this English to Spanish, different language, you can all do compilation, and the compiler doesn't care what language you get in. As long as you can design it, there is a certain way you can do translation. it had no limit of what language it should come from and what language you should end up with. The technology is the same. You just need to define the grammar rule in a proper way to accept it. Now, the third one is hybrid. Hybrid, the good example is the Java language. You basically take in your source program, you put into the intermediate format, say in Java it's called bytecode. And then the bytecode, when you got the bytecode, you would have virtual machine, and then the virtual machine will interpret it into output. So that actually is interpretation. And the front end, you compile from Java language to bytecode. That's called compilation. So modern language try to have the combination of a compiler and interpretation hybrid system. And also because of this, we can make the main idea of having this is the machine independence. So basically, the Java program compiled into bytecode, but here the bytecode is shared by different machines. I can send this bytecode to different person as a .jar file, JAR jar file, and then that jar file can be done by the interpreter on Mac OS or on Windows or on Linux. So the bytecode actually help Java to become platform independent. It doesn't depend on any platform. So this is called hybrid model that translates from source code to intermediate code or bytecode and then go into virtual machine. And because of that, the just-in-time compilation is invented. So you don't compile the code into your local native machine language, say your i7 assembly code instruction set. You don't compile it. You don't really compile it until you can no longer wait. That is called just-in-time compilation. You keep it in a format that's shared by different machines. Until the last moment, you need to execute it on your own machine. We call it just-in-time compilation. Okay, we skip this one. This is a command. You can go back to check there. So the compilation strategy, we have mixed compilation and interpretation. So compilation strategy, every language may use one or more compilation strategy. Here are examples. So we have three main models. Here we will talk about the compilation strategy, and each strategy has some advantage and disadvantage. The first one is the preprocessor called tokens. Some language like C, C++ has the preprocessor that help you to remove the command and white space and group characters into tokens, and then expand abbreviation in the style of macro assembler, identify the high-level syntactic structure like loop subroutine. So that's called a preprocessor. And preprocessor is useful in C, C++. And in fact, in early day, the C++ language is only a language with a preprocessor feature. So C++ language basically will be processed by a preprocessor into C language. That's the early day implementation, but nowadays it's different. And different preprocessor derivatives perform different tasks, like including the include, punch define, punch undefined, punch if, punch else if, punch end if, punch if defined, punch if not defined, and other like punch error, punch line, and punch pragma. So these are the different derivatives for preprocessor that happen before your compilation. And so you have a preprocessor compilation and then link and go. So it's a compiling go process for C and C++. And second one is a library routine and linking. So for Fortran language, you compile it into a certain machine code format and you link with some library. And this library routine may be written by Fortune, may be written by C++. So with the linking and library routine, you can actually have a mixed language environment. So that's the second strategy. The first one is pre-processing. Second one is the use of routine and linking. But both of these still are old concepts. Number three, post-compilation assembly. So there's another way. You just compile it into assembly code. And then different language like Ada compile to assembly code. And then your C++ can also compile to assembly code. And your Prolog may be compiled to assembly code. And later you assemble together to provide language. This actually is not as popular now. It's also an old idea. But nowadays, people don't do a post-compilation assembly. Instead, people use the Java virtual machine. And on top of Java virtual machine, actually, there are more than 200 different programming languages. Everybody compile their language into a bytecode. And that bytecode not only from Java, but can also be from different language. They all run on Java virtual machine. So theoretically, you can also compile C++ into a Java code, bytecode, and then run on same Java virtual machine. The C preprocessor conditional compilation. You compile, you preprocess into modified code, and then you compile it. So this is called C preprocessor. Delete portions of code which allows several versions of program to be built from the same source code. And E, source-to-source translation. So instead of compile to machine code, you can compile some code to different language and then something like that. So you actually compile to different language and then use that language. For example, we use C as a target high-level language. We compile C++ into there. We compile Prolog into there. It's also possible to have the source-to-source translation. That means you do compilation from one source language to another source language instead of the machine code. F is bootstrapping. Bootstrapping is similar to Java virtual machine, but because this only useful for Pascal, and actually it is almost obsolete. So we won't go into detail for the bootstrapping over here. But the idea is similar to a virtual machine. So you can run a program, and then you match the machine code interface, something like that. Okay, we won't go into the details for Pico. It's already old. So now interpretation strategy. The previous one we talked about the compilation strategy. Now we look at the interpretation strategy. So we compilation of interpreted language. So basically, I have a Python file. I can also compile it into an intermediate code called PYC code. And actually, it was made possible as a library for people to copy and use it. So, and in turn, actually, Python interpreter has an option for you to check, and then you can actually generate only the PYC code and make it portable for other platforms. So it actually similar to Java machine. You can put it into certain intermediate code called bytecode, and then there is a Python virtual machine can handle it. So Python nowadays also accept this bytecode idea to make it portable and machine independent. Okay, that's a good strategy. And then last one, dynamic and just-in-time compilation. Basically, you try to keep it in bytecode until you cannot wait. You have to run it. So basically, just-in-time compilation is compilation at the runtime. So this is also called the interpretation stage for Java language or Java virtual machine. And it's mainly adopted by Java language, C# compilers, .NET intermediate language. This is Java just-in-time compilation. as I mentioned it already. Microcode. Microcode is assembly level instruction set. Actually, you have the instruction, and originally you need to execute it one by one, but actually you can expand it into microcode memory, and then microcode is just like a tiny program. So you get an instruction, you decode it, and then call some subroutine type of a microcode from the memory, ROM. So it's instruction translate into microcode and call microcode to do some real job. So microcode is just like a assembly level of the subroutines. So this is another interpretation that's done in chip level. So this is a 4-bit nibbler CPU. You get the instruction. So here is the instruction: any jump C, jump C, jump NC, jump NC, compare I, compare M, little n, whatever it is, are instruction. So this instruction, once they arrive at the decoder, they will actually be translated into microcodes. That is, and each microcode with the clock control would be controlling the data path. So this microcode can be considered as a tiny program that you get a functional call like JC, and then it will be interpreted into this microcode, and microcode control the data path in your microprocessor. And this is a example for nibbler 4-bit CPU. So it actually is also a example for interpretation. So this I will skip. Programming environment. So our programming environment including the operation system. So here is one example given by Unix. So you need to have editor. You need to have pretty printer to make it prettier in some format, preprocessor, you have a debugger, style checker, and module management, version management, or a lot of things, Git or something. But these are in Unix. And nowadays, actually, these are considered as old-fashioned tools, but still in use. And we have the editor, Notepad double plus to support different language. And we have the make program to build a program to make the version control. And we have the version control, RCS, revise control something. And then now we have Git and GitHub. And the whole thing can be combined into something called integrated development environment, IDE. And nowadays, actually, we no longer check into those detailed tools, like the Unix style, find your tool one by one. We no longer do that. Actually, we just pick a whole package by the IDE. We pick Eclipse or Nepin or Komodo or something, or your Visual Studio, Android Studio, Xcode developer. You pick one environment and you can support a lot of different language. That's what we have right now. It's called integrated development environment. And there are cost issue, language support issue. Eclipse probably is the most popular one now, but it actually suffered the performance issue. And I use a lot of IntelliJ IDEA tool, for example, like PyCharm for Python. Okay, now we have a short interview for the 6 stage for compiler design. So first, we still need to have some knowledge about the background for compiler, the computation model. And there are 6 phases for compilation: lexical analysis, syntax analysis, and then semantic analysis, intermediate code analysis, generation, code optimization, and code generation. Code generation is for machine code, not the intermediate code. So these are 6 stages, and all these 6 stages, we need a simple table. And for us to study in this course, we will introduce up to the semantic analysis. From chapter 1, 2, 3, 4. For 2, we will cover lexical analysis and syntax analysis. Chapter 3, we talk about the type checking. Chapter 4, we talk about the semantic analysis. Chapter 5, we cover lightly about the intermediate code generation. And the first stage is scanning. As I say, it's a token, and I will try to give a extra section on tokenization as I promised for using the Python example. And I'll try to find a time to schedule it as a talk. And here is tokenization. Second, we actually try to have the knowledge of the DFA, deterministic finite state machine. So from the token, we actually build a finite state machine to analyze the input language or file, whether it is accepted by a Java language or not. This is the design for a deterministic finite automata to design a machine to decode. So that finite state machine is used to parse the language to adapt the grammar that defined by context-free grammar to do syntactical analysis. This is for the second stage. And we will have a more detailed introduction in starting of chapter 2 about syntax analysis. So here you just need to remember, first stage we take in the token, second stage we analyze the syntactical data from that tokens, stream of tokens, and to pass it into a syntactic tree. And we actually will have the push down automata to help us to build it. And this is called the LR parser. So, and after that, we go into the semantic analysis. The second stage called syntactical analysis. It's just like checking the grammar. And semantic analysis is checking the meaning. So something follow the grammar may not make sense. So semantic analysis will be checking the semantics. For example, do you have the you assign the right data format or not? For example, you declare a double variable and then whether it's accepted by Java language or not. And that fourth stage is the intermediate code. So intermediate code can be a bytecode or different format. And in the old day, we call it intermediate code. And right now, some language like Java, actually the compiler stop right here because it's actually a intermediate code format called bytecode. And after that, it can be executed by different machine. And last 2 stages is code generation. So actually it's optimization and code generation phase, the 2 last stage. And this one is machine dependent. You basically take in the intermediate code, for example, like bytecode or something, and then you actually optimize it to make sure that your data path run the fast on your CPU. And the last stage is to generate real machine code for the machine to run. Okay, and during the 6 different stages, we all need a simple table to keep track of the ID and variable and values. So now we are on the overview of front-end compiler design. So the previous 3 stages, we call it front-end. That's the scanner, parser, and semantic analysis. And we only cover these in this course. And back-end is machine dependent. We don't have enough time to cover all of them. So this first 4 chapters, we are dedicated on the front-end for compiler. And here is a C language for GCD. We mentioned this before. And that is a source program. We will actually take it in as a tokens. And the token is the smallest program unit. So each one we actually is like this. It would go into like tokenize. Each one of them is called a token. And then based on that token, we analyze by the C grammar, and then pass it into a parse tree. So that grammar is described by BNF, eBNF, those kind of things, and context-free grammar to define your language and pass it. So the end result we have is right here. And our chapter 2, 3, 4 will be dedicated for here. And right here, I just tell you, these are a simple example, and actually that's what we are going to do for the chapter 2, 3, 4. Like this. That simple GCD will be compiled to using the parser to generate like this. Okay, the last lecture, the development of programming language. So basically, the development of programming language, we started from finding a good computing model, Neumann, lambda calculus, logic, neuron, or DNA, and then we find a paradigm. Whether we want to do block programming, pair programming, script programming, signal/slash programming, logic programming, whatever paradigm we pick, then we design a language. What keyword we need to have, what data type, what data structure we support, flow, and then OOP issues, and then we go into compiler design. So basically, this course we mainly focus on the blue one and green one. And green one, we only cover the front end, the top 3 stages. But in terms of knowing development of the whole programming language, the topic is these 4, including language design, compiler design, programming paradigm, and the programming model. We focus on language design and slightly on compiler. So these 2 topics are our main focus. And this actually is supporting the language we actually is in Unit 3, but we actually not covering that much. And Unit 4 is on this part for hardware, but we don't have time to go to there. So the computing model that we have, including neural model, including neural network, including lambda calculus, logic programming, neural network, and then DNA computing, and then color processing, mechanical computer. So the programming paradigm are so many. You have different style over here. So here is more imperative, object-oriented programming, different families. So here we have descriptive language, first-order functional programming language, functional programming language, imperative. So here you have imperative and functional, 2 different branch. Here is purely imperative language. So this one gives you the overall view of different principal programming paradigms. And you pick one paradigm and you find a language and use that for certain applications. So runtime environment including we actually like C++, we starting from programming essential, talking about structures and then object, and then whole development kit issues. If you pick a language, you need to know the basic structure, the object-oriented programming features, and then the whole development kit and API issues, and then design framework, client-server programming model, and design studio. So this whole thing is after you pick a language, then you need to find a runtime environment and development environment. That's how you choose a whole language and its supporting system. So here I finished chapter 1. Let me check if Daniel's still around. And any question for him? Okay. Any question today? Oh, actually, he left already. Okay, so this concludes my talk, and then I will provide a recording and put on our website. Thank you. Bye now.